right, I think we're going. So Adam obtained his bachelor's in mathematics and master degree, where he specialized into quantum computing at the University of Cambridge, graduating with the Mayhew Prize. He's currently working with Dr. Xie at the Hon Hai Research Institute and with Dr. Strelchuk at the University of Cambridge. His research interests include quantum locally testable codes.
Thank you very much. Thanks for having me. It's a real pleasure to speak. This is general distance balancing for quantum locally testable codes. Work is co-authored with David Lin and Min-Shu Xie. And you can find it on the arXiv here. Let me get a laser pointer. You can find it on the arXiv here, and we've also submitted to AQIS. Questions are encouraged throughout. Please interrupt me. I'm very happy to have a back and forth with anyone. So let's get started. I'm pretty much going to stake the aim of this talk as being explaining to you this figure and why it gives us interesting quantum error correcting codes. And so I'm going to want to tell you where it comes from, what it tells us, and why we care about it. And in order to do that, I'm going to have to give you quite an enormous amount of background, I'm afraid. Most of the talk is going to be background in classical and quantum error correction, starting more generally and moving towards more specific things. And along the way, I'm also going to tell you the problem that we want to solve, that we and many other researchers want to solve in a broad sense, and that's the qLTC conjecture. And I'll tell you that of the steps that we take towards solving that, or perhaps more accurately, the problems that we solve in that general area. So background, problem we want to solve, and what do we do about it? So as far as the background goes, this is the general roadmap. So the only thing I'm taking as a prerequisite is stabilizer codes, although even that I'm going to recap, if only briefly. And so stabilizer codes is going to lead us on to CSS codes, which are quite a simple special case of stabilizer codes. And from CSS codes, I'm going to display the homological description of CSS codes. But I'm not going to be able to do that without first taking a detour into classical coding theory, specifically linear classical codes and their parity check matrix formulation, which may be familiar to a lot of people. And then lastly, I'll be able to talk about local testability. So that's our background roadmap. So starting with stabilizer codes. As many people will know, the idea with a stabilizer code, or in fact any quantum error correcting code, is to encode some number of logical qubits, so let's say k logical qubits, into a larger number of physical qubits, n. So you're adding redundancy, and so that's the idea. You protect from noise by adding some amount of redundancy. And so you're doing that by encoding these k logical qubits into some subspace of the n-qubit Hilbert space. And they're encoded into that subspace, and that subspace is called the code space. So the code space is the space of allowed states. So if you move outside of the code space, then for sure there's been an error. If you're within the code space, then perhaps there hasn't been an error, or perhaps there's been a logical error that's moved you to some other part of the code space. So these code spaces can take a lot of different forms, but in the case of stabilizer codes, these code spaces are defined by a bunch of Pauli operations, and they're defined to be a simultaneous +1 eigenspace. So this is why we call them stabilizer codes, because we're thinking +1 eigenspace, these Paulis stabilize the code states. And indeed, if we pick n minus k independent, permission, and commuting Paulis, then we will be able to encode k qubits into n qubits for some n greater than k. And I want to emphasize this commuting condition here. This is going to be very important for us as we move forward. So let me give a famous example now. This is the Steen 7-qubit code. This has 6 independent Pauli stabilizers here. So you would read this on n equals 7 physical qubits. Let's say this first one is going to be Z1, Z2, Z3, Z4. This second one, Z1, Z2, Z5, Z6. And there's 6 independent permission and commuting Paulis on 7 physical qubits. So this is going to encode k equals 1 logical qubit. And so what operations are there that are going to keep us within the code space? So, well, let me talk about how we tell whether there's been how can we tell whether there's been an error? What we'll do is we'll measure every stabilizer. So we'll measure Z1, Z2, Z3, Z4, Z1, Z2, Z5, Z6, and so on. And if we get +1 for all of them, then we know that we're in the code space because it's the simultaneous +1 eigenspace of all of these. If we get -1 for any of them, then we know we must be outside of the code space. Indeed, if a Pauli operation occurs on our code state and it anti-commutes with, let's say, this first stabilizer, then we will for sure measure -1 on that stabilizer. And so the operations that we cannot detect are exactly the Pauli operations that commute with all of our stabilizers. And there'll be two types of those. There'll be the stabilizers themselves, which have no effect, and there'll be the logical operations, which commute with all of our stabilizers, but are not themselves stabilizers. And those are the dangerous ones that we want to avoid. But we can lump them all together into the so-called undetectable operations for now. So if that's all right, I'll move on to CSS codes, which are a generally fairly, at least for now, non-threatening specialization of stabilizer codes. So these are just stabilizer codes in which every stabilizer contains either all X or all Z. So no Y's at all. And every stabilizer must contain only X's and only Z's. So there's no mixture. And so an example, again, is the Steen-7-qubit code, where you can see here, these first three are all Z, these last three are all X, so we can split them. And we can write them in these two separate matrices here. I do want to make one comment, which is that this Steen-7-qubit code is special in that you can obtain the Z generators by replacing X with Z in the X generators and vice versa. And that doesn't need to be the case in general. In fact, in general, this can be very, very far from being true. This just happens to be true in the case of the Steen-7-qubit code, that it has the same form of the generators on each side. And so why are we considering CSS codes? The first reason, the reason I suppose we're allowed to, is it's not very restrictive to just consider CSS codes within the class of stabilizer codes. There is in fact this result that takes any stabilizer code and turns it into a CSS code and only incurs a constant factor hit on all of the things we care about. So the length of the code and the dimension and the distance and things like that. And because we are only going to care about asymptotics, it really isn't a restriction to only consider CSS codes within stabilizer codes. And then the reason that we want to, that's the reason that we can, the reason that we want to consider CSS codes only is because they're going to admit this really nice homological formulation that I'll go on to talk about later. Good, so let's talk a little bit about classical coding theory. So the situation is quite similar here to in the quantum case. We have k logical bits, and we want to encode them into some larger number of physical bits by adding redundancy. And again, the allowed space of code words, which forms a subspace of the vector space of the n bits, is going to be the code space, and that's the space of allowed words. So a well-known example will be the 3-bit repetition code. And you, as you would imagine, just repeat each bit 3 times. And this is going to protect from the effects of noise by taking a majority vote. So if we're assuming that our noise is acting independently on each bit and with some small probability p, then we, after the noise acts on our code word, we might observe something like 0, 1, 0. And then we say to ourselves, it's most likely that that came from 0, 0, 0, so I'll put it back to 0, 0, 0 and decode to 0. And so in fact, you're taking a physical error rate of p, and you're going to change it into a logical error rate that goes something like p squared. So you're better protecting yourself from the effects of noise. Allow me to mention here, because it's going to come up later, that this is the 3-bit repetition code. The t-bit repetition code is exactly what you think it is. That is 0 encoded into t0s and 1 encoded into t1s. Now, so where do parity check matrices come into this? So the parity check matrix is just a quick and compact way of describing a classical code space. So remembering that the classical code space is the space of allowed code words, in this case 000 and 111. The parity check matrix is a binary matrix for which this allowed code space is exactly the kernel. So in this case, this is a parity check matrix because its kernel, and you can check this for yourself, is exactly 000 and 111. Remembering that all arithmetic is being done over the binary field. So for example, if you put 000 here, trivially, you're going to get the 0 vector coming out. And if you put 111 here, then you'll be able to check that we've got 1 plus 1 is 0 and 1 plus 1 is 0. So these parity check matrices give us, as I say, the vector space of allowed code words, the code space being their kernel. So these have a certain number of rows, and we call the rows checks. And each check tells you something about the allowed code words. So this first check is telling us all allowed code words have their first bit plus their second bit being equal to 0. And this second check is telling us second bit plus the third bit must be equal to 0. And so as you can probably imagine, if you have k independent checks or k independent rows, so that's k linearly independent rows, and n physical bits up here, then you're going to get n minus k logical bits. Stated another way, n minus k independent rows, n physical bits means k logical bits. So this allows me to move on to the homological description of CSS codes. So as I mentioned earlier, if you have these stabilizer codes, and in particular CSS codes, the operations that we cannot detect the effect of are going to be those that commute with all of our stabilizers. So let's see what that might look like in the case of the 7-qubit Steam code. And I'll show some examples of undetectable operations. So this is one of X type, and this is one of Z type. So trivially, the one of X type is going to commute with all of the X type stabilizers. And the one of Z type is trivially going to commute with all of the Z type stabilizers. But then you can also check for yourself that this is going to commute with all of the Z type stabilizers, and this is going to commute with all of the X type stabilizers. So they're each examples of undetectable operations. Indeed, you can see that this commutes with all of the Z type stabilizers because it has an even overlap with each stabilizer. So for example, it overlaps with the first one in the first 4 places, with the second one in the first, second, fifth, and sixth place, and with the third one in the first, third, fifth, and seventh place. And so because the overlaps are of even size, you will get commutativity. Again, I mentioned there are 2 types of undetectable operations, the logical errors and the stabilizers. If you know a little bit about the 7-qubit Steam code, you will know this is a logical error, and this is a stabilizer. In fact, it's up here. But we're just lumping all these together for now. Undetectable operations are the things that commute with all our stabilizers. So the idea now is going to be to form parity check matrices from these 2 lists of stabilizers. So we can write down an HZ and an HX. So binary matrices, HZ obviously having 1s everywhere you've got a Z, and HX having a 1 everywhere you've got an X. And I'm just going to mention one more time that the 7-qubit Steam code is a special case because these 2 matrices are actually the same, and that does not need to be the case in general. So now we've got parity check matrices. The code space that they define is going to be their kernel. And so their kernel, you can convince yourself, and we will take a moment to appreciate this, their kernel, their code space represents exactly the undetectable operations of X type and Z type respectively. So if we imagine the binary vectors that are multiplied to 0 by this matrix, those are going to be exactly the binary vectors that have even overlap with every row. And so, for example, the all ones vector 1, 1, 1, 1, 1, 1, 1 is going to be in the kernel of this matrix, and that exactly means that x1 all the way up to x7 is going to be an undetectable operation of X type. And you can convince yourself again that that's true because an X type stabilizer commutes with a Z type, sorry, an X type operation commutes with a Z-type operation if and only if it has overlap in an even number of places, and a vector is going to have 0 inner product with one of these rows if and only if, again, it has overlap in an even number of places. So all we've done so far is we've just formed 2 parity check matrices from our stabilizers, and we've noted that the undetectable operations exactly correspond to the respective code spaces. So what are we going to do with this? Well, let's first ask ourselves, can we just write down any 2 parity check matrices, HZ and HX, and expect them to define a CSS code? And the answer is no, they must satisfy some sort of compatibility condition. And the reason for that is because in any stabilizer code, as I emphasized earlier, all stabilizers must commute. And so quickly going back here, you'll know that all of the Z stabilizers are going to trivially commute amongst themselves. All of the X stabilizers are going to trivially commute amongst themselves. But what we must have is each Z stabilizer commuting with each X stabilizer. So there's actually 9 things to check. This one must commute with all 3. This one must commute with all 3. This one must commute with all 3. So there's 9 things to check. So this compatibility condition corresponds exactly to the commutativity of all of the stabilizers. And that's the same thing as saying that every row of the binary parity check matrix HZ is orthogonal to every row of the binary parity check matrix HX. And that again is just because this is going to commute with, say, this, if and only if they have an even sized overlap. And that is exactly the same as saying the corresponding binary vector is orthogonal to the corresponding binary vector. Remembering that orthogonal here is going to mean with respect to the usual inner product with arithmetic done over the binary field. And so that's going to be the exact same thing as this condition, HX, HZ transpose equals 0. You can imagine you can check if every row of some matrix is orthogonal to every row of some other matrix by just turning one of the matrices on its end, and then you'll be multiplying each row against each row. And if you get the 0 matrix, then you know every row of the first was orthogonal to every row of the second. Now, once we've seen this condition, the homology comes in, because now we're thinking, let's define a chain complex using these things. But what is a chain complex? That is absolutely something I need to explain. So there's, I suppose, quite a high-level definition of chain complexes involving abelian groups and morphisms. But for us, it's not going to be that complicated. Chain complex is just going to be a sequence of vector spaces, Ci, and linear maps Di going from Ci to Ci minus 1, going up and down. And the only condition that we're going to enforce is going to be this Di plus 1 equals 0. You might say that the boundary maps square to 0, where I apologize because I didn't mention there that these linear maps are typically called boundary maps, or sometimes boundary operators or differentials. This chain can be infinite. It can be infinite in both directions. It can be infinite in one direction, or it can be completely finite. And what we're saying now is that a quantum CSS code on qubits can be thought of as a 3-term chain complex of vector spaces over the binary field, where we get this condition of squaring to 0, hx, hz transpose equals 0, being exactly the compatibility condition for the stabilizers. And so this is a representation of a binary quantum CSS code on n physical qubits with n sub x, x checks, and n sub z, z checks, meaning n sub x, x stabilizers, and n sub z, z stabilizers. And you can convince yourself of this by just thinking, well, h sub x is going to have n columns because it acts on n qubits. And then it's going to have n sub x rows. Those are the n sub x, x checks. And then hz is going to map from here into here. So that's going to, again, act on n physical qubits, and it's going to have n sub z rows, meaning the n sub z, z checks again. So at this point, we should stop and ask ourselves, well, why are we doing this? All we've done so far is we've noticed that a CSS code can be written in terms of these 2 parity check matrices that have to satisfy this condition, and that just gives us a chain complex. So up to this point, this is all just notation. But the reason that we want to do this is because we're going to be able to import lots of information from lots of constructions and results and experience from algebraic topology and homology theory, and to a lesser extent geometry. But before I go on to talk about some of those more homological constructions, let me talk about some parameters of code, all of which you can extract from the chain complex representing the code. So the important parameters for now are going to be dimension, distance, and locality. So the fourth parameter, soundness, I'm going to go and talk about when I come on to local testability. But for now, the important parameters are dimension, distance, and locality. So dimension and distance will be most familiar to people. Dimension is simply the number of logical qubits encoded. So that was the K I mentioned. So K logical qubits encoded into N physical qubits. The distance is then the minimum weight of a logical error. So that's a logical error is then a Pauli error that commutes with all the stabilizers, but isn't itself a stabilizer. So it does move you to some other part of the code space, and it does that because it cannot be detected because it commutes with all the stabilizers. So you want that to have high weight, because making reasonable assumptions about your noise, you're thinking, let's say roughly that the noise is acting independently on qubits and it's fairly unlikely, then high weight errors like these logical errors are, we hope, going to occur less. That's the idea. I will also mention that there are two types of distance in the case of CSS codes. There's the X distance and the Z distance, and you can imagine that those are exactly the minimum weights of a logical X-type operation and a logical Z-type operation. And we can think about those completely separately, because any Pauli can be written as the product of a pure X Pauli and a pure Z Pauli. And so we can decode pure X operations and pure Z operations completely separately. And so we say X distance, minimum weight of a logical X-type error, Z distance, minimum weight of a logical Z-type error. And then the overall distance is going to be the minimum of those two. There will be more on X and Z distance shortly. Locality might then be a little bit less familiar to people. So locality is going to be do with, for now, fault tolerance. And so the idea is this: imagine you have a check, a stabilizer check that acts on a large number of qubits. If that check is errorful, then it's going to spread errors to a large number of qubits. And similarly, if you have a qubit that is acted on by a large number of stabilizer checks, then if that qubit is errorful, it's going to spread errors to a large number of other qubits. So the idea in calculating locality is to look at every check and look at the maximum number of qubits involved in some check, and then look at every qubit and take the maximum number of checks that act on a qubit, and then take the maximum of those two. So this actually corresponds exactly to the maximum of the row and column weights of hx and hz. So the idea, we want dimension to be large, we want distance to be large, and we want locality to be small. But we're only going to be able to reasonably talk about the size of these things by defining a family of CSS codes. So we define a family of CSS codes on n physical qubits, and we let n go up to infinity. So we have a whole family of them. And then the best scaling that we can get is going to be linear for dimension, linear for distance, and then constant for locality. So not actually scaling at all. And so that's in terms of the number of physical qubits n, dimension optimally can scale something like n, distance can scale something like n, and locality can just stay constant, so not scaling with m. And then the qLDPC conjecture was the question of whether it was possible to obtain these three scalings optimally for some family of CSS codes. Does there exist a truly optimal quantum CSS code? And this was answered in the affirmative in 2021. And it was a little bit of a road to get there. It was some 20 years of effort to make this happen, starting with the surface code, but it was solved in the affirmative in 2021. And I will also mention that the equivalent classical question, So in the classical case, can you get linear dimension, linear distance, and constant locality? That's a much easier question and has actually been known in the affirmative for, I think, at least 50, if not 60 years. So now moving on to local testability, as I mentioned, that's going to be our fourth parameter, soundness, that we're going to care about. Soundness is, roughly speaking, a measure of local testability. So what is local testability? Well, the motivating question behind local testability is going to be this. Can we test if our state is in the code space by acting on a very small subset of the bits or qubits? And by very small subset, I mean a very, very small subset, even of constant size. So this is our motivating question. So can we tell by only looking at some very small subset of the physical bits or qubits whether we are still in the code space or not? And so this is quite a roughly phrased question for now, and it's something that we're going to make more precise as we go on. And I'm going to show you the definition of soundness in the classical case now. It's a slightly large definition, but we'll work through it. So for us, in the classical case, if you have a code defined by a parity check matrix H, which has m checks and acts on n physical bits, it is locally testable with soundness rho if for every n-bit string x, this equation holds. So what does this mean? This is the Hamming weight of hx. So that's the number of violated checks. So the number of checks of h that x violates. So the number of violated checks divided by n is going to be at least rho times this thing, dx cur h, divided by n. Now this dx cur h is the distance of x from the code space, remembering that the kernel of h is exactly the code space. And the distance of x from the code space is intuitively going to be what is the minimum number of bits of x that I need to flip in order to put myself inside the code space. So if I need to only flip a few bits of x to put myself in the code space, then intuitively this is going to be a vector that is close to the code space. And similarly, if I have to flip a large number of bits of x in order to put in the code space, then I'm saying that it is far away from the code space. So this definition so far says for any x, the number of checks it violates divided by the number of checks is at least the soundness times the relative distance of x from the code, which is just the distance of x from the code divided by n. So that's all a bit of a mouthful. Now, what does it have to do with this question up here? So we wanted to test if our state was in the code space by only acting on some small subset of the bits. What does that have to do with this? Well, one way of going about doing this is testing if the state is in the code space would be by taking some randomly chosen check from H and seeing if that check is violated. So you just take one randomly chosen row from all of the rows of H, and you see, is that particular check violated? And if you do that, if you take a randomly chosen check, it will be violated exactly with this probability, because the number of violated checks is the Hamming weight of hx, and the number of checks is m. And so what we're saying is that looking at a random check will show us that our word x is not in the code with probability at least the soundness times the relative distance of the word from the code. So what we're seeing now, we're starting to see a little bit more how this works. We're seeing that if our word is far from the code, then this soundness condition means that we are increasingly likely to see a violation of a check when we look at a random check. But we still haven't exactly what we've got. We still haven't got exactly what we wanted up here. So the idea is that if rho is itself constant, then by only looking at a constant number of randomly chosen checks, we will be able to determine with constant probability whether our code is, whether our word x is in the code or far away from the code. And by far away from the code, I mean that this relative distance is a constant. So let me say that again, because that was a bit of a mouthful. If we have a constant rho, a constant soundness here, then it suffices for me to look at a constant number of randomly chosen checks. And by doing that, I'll be able to see with constant probability whether my word is in the code, cur(h), or far away from the code, meaning that this relative distance is some constant. Now, that's all very well and good, but so far this is only talking about looking at a constant number of checks. What I promised was a constant number of bits. And in order to convert from a constant number of checks to a constant number of bits, I must talk about locality. So if I have constant locality, what that means in the classical case is that simply put, each check only acts on a constant number of bits. And so if I was acting on a constant number of checks, that would automatically mean that I'm acting on a constant number of bits. And so indeed, if we have constant soundness and locality, then we can achieve that task by only acting on a constant number of bits as desired. So to say it in full, if you have constant soundness and locality, then you can look at a constant number of randomly chosen checks, and that converts to acting on a constant number of bits. And by doing that, you'll be able to determine with constant probability whether you are in the code or far away from the code, meaning that your relative distance from the code is a constant. And so that is the full statement, the full more precise version of the question that we had earlier. So what is the notion of soundness in the quantum case? Well, there is a whole notion of local testability in the quantum case for any quantum error correcting code, and it's far more involved. And it specializes somewhat to the case of stabilizer codes. And then it specializes even further to the case of CSS codes. But we can just say for simplicity, and this is going to be avoiding some details and some constant factors, but it's going to get the point across that in the case of CSS codes, you take the soundness of the two classical codes that define it, so the one defined by the parity check matrix HX and the one defined by the parity check matrix HZ, and whichever of those has the worst soundness, then again, up to constant factors, that will be the soundness of our quantum CSS code. So you can get good soundness on your quantum CSS code if and only if you have good soundness on the two classical codes that define it. So that's going to be the aim of that. And so then the qLTC conjecture is asking whether we can get quantum CSS codes that have simultaneously optimally scaling dimension, distance, locality, and soundness. So can we get our soundness all the way up to a constant in the quantum case? And this is open. The equivalent classical question for this one, the C³ conjecture, is known to be true, but was highly non-trivial and was solved fairly recently in 2021 after several decades of effort. And before I move on, allow me to say a few more words about the importance of local testability. It is known to be of a significant theoretical interest in the classical case, and the hope is that it will be similarly important in the quantum case to quantum complexity theory particularly. The notion of classical local testability was used extensively in the proof of the PCP theorem, which is one of the most important theorems in classical complexity theory. And it is hoped that perhaps the notion of quantum local testability could be similarly helpful in perhaps converting a qPCP conjecture to a qPCP theorem. Although I wouldn't be doing my due diligence if I didn't mention that a direct quantization of the proof of the PCP theorem from classical locally testable codes actually fails. And so it is open whether quantum locally testable codes can give you a quantum PCP theorem. Even so, it is highly suspected that quantum locally testable codes will be of great theoretical importance going forward. So what previous constructions are there of quantum locally testable codes? Well, there are 3 papers that deliver us quantum locally testable codes, and I'm showing 2 of them here. So there's one due to Hastings, who presents the hypersphere product codes, and there's one due to Leverrier, Lond, and Zemmour, who present the hemicubic codes. And I'm putting them together because they have quite similar parameters. And so these are their parameters. So this is the optimal scaling of everything. So in terms of n physical qubits, then the qLTC conjecture requires you to get constant soundness, linear distance, linear dimension, and constant locality. And as you can see, they have fairly similar parameters. They both have pretty good, very good soundness, polylogarithmic away from optimality. They also have very good locality within a logarithm of optimality. And they have a good distance as well, being a square root. And then they both suffer from having a constant dimension, which I should mention is in some cases not a problem. There are situations where you would only be interested in soundness, distance, and locality, and you're happy to sacrifice dimension. If you know a little bit about the NLTS conjecture, then you'll know what I'm talking about. But for a full-blown qLTC to solve the qLTC conjecture, you need all of these 4 parameters scaling optimally. So the third work that constructs quantum locally testable codes is called Quantum Locally Testable Codes with Exotic Parameters, due to Cross et al. From September of last year, so quite recent. And they provide us with 4 constructions of quantum locally testable codes in the form of their theorems 1.1 up to 1.4. And something that you'll immediately notice that is different about the last 3 of these is that there appear to be 2 variables, and there are. So, for example, here you can allow n1 and n2 to separately vary, and that will give you a whole collection of different codes. And you can find examples of these codes, or examples of this collection, by substituting in values. So, for example, if you want capital N physical qubits, then you could set, let's say, n1 equals square root capital N and n2 equals square root capital N. And then you'll be able to read off things like square root locality, linear dimension, things like this. So there's a lot of information written here, and I want to guide you through all this information let's first point out that the dimension is generally very good. The dimension is linear, or sometimes straying a little bit away from linear, but all of the dimensions are scaling, and that is an improvement over the previous constructions. But they suffer from this. Soundness times distance over locality is always a constant. And so what do I mean by this? Well, the latter 3 constructions all arise as consequences of their theorem 1.1. So they construct their codes in theorem 1.1, which have optimal soundness, optimal dimension, optimal locality, but a constant distance. And then in order to raise the distance, they have to sacrifice either locality in the case of theorems 1.2 and 1.4, or soundness in the case of theorem 1.3. And so as distance rises, they have to sacrifice either soundness or locality. And this quantity soundness times distance over locality is an important one to consider in the theory of local testability. And it's something that we might want to require to be greater than a constant. In fact, for a full-blown quantum locally testable code of fully optimal parameters, that will of course be linear. And so we do want to consider the regime just as an example of a parameter regime that you consider. We do want to consider the regime where this is super constant. So this is scaling. And the last thing I will mention, because it's important to us, is that theorems 1.3 and 1.4 use the notion of distance balancing. And in fact, they distance balance theorem 1.1 to get these results. And distance balancing is something that I will go on to talk about now. So this is the second roadmap of background material, and I promise it's the last one, and definitely shorter one. And so we just need to talk about distance balancing before we can look at our results. Distance balancing is something that you can do to a quantum CSS code if you want to get other more desirable parameters from it. So I'll talk about what distance balancing is, how it's done, then I'll talk about some results on it, what actually happens to the parameters when you distance balance, and then I'll talk about specifically local testability and soundness under distance balancing. So starting with just distance balancing. Distance balancing, as the name suggests, addresses the situation in which we have a CSS code which has a bad x distance, but a good z distance, or vice versa. So you have a bad x distance and a good z distance, and your overall distance, which is what you care about, is the minimum of those two. So you can improve the distance by evening those two out. And again, it can be done both ways. So as I say, during distance balancing, the two distances are evened out. So I'm going to talk in a second in quite painful detail about how distance balancing is done. But let's just start by saying that it uses a homological product construction. So this is why we were writing, in this talk at least, why we're writing quantum CSS codes in terms of chain complexes. And it's so we can take the homological product, which is an operation from algebraic topology, which I'll go on to talk about. And what we're going to be taking the homological product of is the chain complex of the quantum CSS code that we want to distance balance, with the chain complex of some classical code that we're going to be using to do the distance balancing. So we have the quantum CSS code that we want to distance balance, and then we have the classical code that has some desirable properties that are going to be useful to us. But this immediately might look a little bit confusing because I haven't said what the chain complex of classical code is, but it's really quite trivial. Any classical code with a parity check matrix H, we can write down a trivial chain complex as just two terms. So this would be a parity check matrix H acting on T physical bits and with S rows or S checks. And so this is then just a two-term chain complex. And I should mention as well, as I say, we will be using some classical code with desirable properties to do this distance balancing. The ones that we are going to be using are going to be either the T-bit repetition code, that would be one case, and the other case we will consider will be a fully optimal good classical LDPC code. So linear distance, linear dimension, and constant locality. So we're going to start distance balancing by writing the quantum CSS code that we want to distance balance and the classical code that we're going to use to do the distance balancing. We're going to write them both as chain complexes. So the quantum CSS code is going to be written as a three-term chain complex, and the classical code that we're going to use is going to be written as a two-term chain complex, as I mentioned. So the second step is going to be write the dual of the classical code chain complex. And the dual is a simple homological operation where you take your chain complex and you just reverse the order of the spaces, and then you take the dual of all the linear maps. So in this case, where we have an explicit parity check matrix H, the dual will be instantiated by the transpose. So the dual of R is very simple in this case, it's just that. The third step is then to take the homological product of C with R star to get this figure, which I promised you. Except I haven't really told you where this figure has come from. I haven't told you what it means or why we care about it. So I will tell you where it comes from in a second. I'll give you the actual formula for the homological product. But first of all, let me tell you how to read this. So the homological product of the chain complex C with R star is written as C cross R star, and that's a new chain complex. In fact, this is a four-term chain complex. So we took the product of a three-term with a two-term chain, and we got a four-term chain complex. So this chain complex C cross R star has four spaces: C cross R star 3, C cross R star 2, C cross R star 1, and C cross R star 0. And therefore three linear maps going between them: D3, D2, and D1. So how do you read off these spaces from this diagram? Well, you sum vertically. So let's take C cross R star 3, and that's going to be just this space, F2 to the N Z tensor F2 to the S. C cross R star 2, as I say, you sum vertically, that's going to be F2 to the NZ tensor F2 to the T, direct sum F2 to the N tensor F2 to the S. And one more, C cross R star 1 is going to be F2 to the N tensor F2 to the T, direct summed with F2 to the NX tensor F2 to the S. And then this is just going to be that. So those are your spaces. So as I say, you just direct sum vertically. And then the linear maps can be recovered also by looking vertically and by summing as appropriate. So for example, E1 is a map from C cross R star 1 into C cross R star 0. And C cross R star 1 is the direct sum of this with this. So if you've got an element in C cross R star 1 and you want to see how D1 acts on it, then you just take that element as the direct sum of something in here with something in here. You act with HX tensor I on here. You act with I tensor H transpose on here, and you sum the two together, and that gives you D1. And so the same is true of D3 and D2. You sum, you act as appropriate, and you sum as appropriate. For example, D2 would be by far the most complicated, and you would take something in here, so this, direct sum with this, and the thing in here, you act with HZ transpose tensor I, and then you add that to I tensor H transpose acting on the thing in here, and then the result, the thing in here, is going to be HX tensor I acting on the thing in here. So that's D2, and similarly D3 can be recovered from those. So that's how you read this diagram, but I still haven't told you where this diagram actually comes from. We know it's the homological product of C with R star, and that gives you C cross R star. But how do we actually recover this diagram? And well, this is the formula for the spaces. So C cross R star sub P is going to be the direct sum from I equals 0 up to P of the ith space of C tensored with the P minus side space of R star. So for example, if you put P equals 0, Leandro, your hand is up.
Yeah, can you hear me?
Sorry, is that a mistake or is there a question? You might be muted, Leandro. I can't hear
you. Can somebody help me and kind of speak up a little bit?
I don't know if you're speaking, Leandro. I'm sorry, I can't hear you at all.
Yeah.
Yes, I'm afraid I can't hear you, Leandro, at all.
So can you hear me? Besides Leandro?
Hopefully, if I perhaps go into the Teams chat, then there we go. Yeah, no, I'm looking at the chat now. I don't know if there's something wrong with my audio. I'm afraid I can't hear for some reason. I'm assuming you can hear me, or you would have told me. I'm not quite sure why I can't hear you. Well, I'm happy for you to ask your question in the chat then. We can work out the sound issues later. I just want to ask what the sub-index means. X index. So the sub-index on the spaces. So for example, C sub I and R star sub P minus I. Is that it? Gotcha. Yeah. So let me go back. So those are just the spaces. So in this case, you have C cross R star sub P, and then those are the spaces C cross R star 3 to 1 down to 0. And then C sub I is going to be the ith space of C. And it's a good question, and I should have written this. Those will then be the 3 spaces of C. So you'll have C sub 2, 1, and 0, and then R star is going to have spaces R star sub 1 and R star sub 0. Hopefully that answers your question, and I can show you an example of this. So for example, C cross R star 0, so setting P equals 0 in this, is going to be C0 tensor R star 0. And so that's going to be just F2 to the NX tensor F2 to the T, and you can see that's exactly what we have in the diagram. Setting P equals 1, then you're going to have C1 tensor R star 0. So F2 to the N tensor F2 to the T, that's that. direct summed with C0 tensor R star 1, so F2 to the NX tensor F2 to the S. So that's that exactly there. And similarly, you'll be able to see that P equals 2 and P equals 3 give you what you have in the diagram. So hopefully that answered the question. I don't know why I can't hear you, but please feel free to raise your hand again if there's any questions. I'm happy to take them via the chat or otherwise. But I'll move on for now, assuming everything's okay. So given this definition of the spaces, the boundary maps then follow in the natural way, as I described earlier. So it just requires you to write down all of the natural maps going between the spaces. So for example, this one, you're looking at F2 to the n Z tensor F2 to the S and F2 to the n tensor F2 to the S. And you will have an identity on the second one. And then you'll see from this one to this one, you have HZ transpose. And that's how you would write down this diagram. You'll always have something tensor the identity or identity tensor something. And then, as I described on the previous slide, you would recover these linear maps by just summing vertically as appropriate. The final step is just to take the last 3 terms of the chain complex, so C cross R star 2 down to C cross R star 0, and use them to define a quantum CSS code. Because you may remember that a quantum CSS code is only a 3-term chain. And you can take any 3 contiguous terms or any number of contiguous terms from a chain complex and use them to define a new chain complex. And so from this 4-term chain complex, we can just take the last 3 terms, and then that will define a new chain complex. And because it's 3 terms, we can define the quantum CSS code from that. So to summarize, the distance balancing procedure is just done with a quantum CSS code and its chain complex. You take a useful classical code that is useful for your situation. You write down its chain complex, you take the dual of it, you take the homological product of those 2, and then you take the last 3 terms of the result. And so what actually happens to the parameters when you do this, what I've promised so far was some sort of balancing of the 2 distances. Before I give those results, I have to mention this important technical caveat, which is that you can only use classical codes that have a parity check matrix with independent rows. This is not a restriction for us, but it is an important technical caveat to mention. So these are the results when you do distance balancing. So when you distance balance, and this is omitting some important details and some constant factors, this is just to get the point across. So the first thing is that the number of physical qubits multiplies with the number of physical bits here to give you the new number of physical qubits in the resulting quantum code. Similarly, the dimensions also multiply. Kc times Kr gives you Kc-Kr, so the dimensions multiply. And then the distances is what we're most interested in. You can see here that you start with distances dx and dz, so that's the x distance and the z distance, and the classical code distance multiplies into the x distance, and the z distance is preserved. And then you might frown at that because what I promised was an improved x distance at the expense of a worsened z distance. But this just appears to be an improvement of the x distance and the z distance stays the same. So this appears to be even better than what I said. But it's worth remembering that the number of physical qubits has increased. And so if the z distance stays the same, then its scaling will actually be worse. And so indeed, you get an improvement of the scaling of the x distance and a worsening of the scaling of the z distance. And then the locality, the resulting locality will just go with the worst of the 2 inputted localities. And then finally, the results on soundness and local testability. So it was shown by Hastings in 2016 that when you distance balancing using the L-bit repetition code, the soundness of the quantum code changes as shown here. So the old soundness goes to the old soundness gets divided by the length of the repetition code. And so this symbol omega means that it is up to constants, at least this. This was applied by Cross et al. To obtain their theorem 1.3. So as I mentioned, they used distance balancing on theorem 1.1. In fact, this theorem 1.1 has optimal soundness, dimension, locality, and it actually has linear z distance, but we have a constant x distance, so the overall distance is a constant. But then they can distance balance this in order to obtain these parameters, and they use the repetition code for that because that was the only result that existed at the time. And so applying this result, they then get these parameters. So then our result is simply a generalization of Hastings' result to all codes. So not just the repetition code, we can then say for all codes, the soundness under distance balancing goes rho to something scaling like rho over the length of the classical code up to constant factors. An important caveat is that, again, the classical code must have independent rows or independent checks, but that's not restrictive for us because we're going to want to apply this in the case of an optimal classical LDPC code or a good classical LDPC code, so having linear dimension and distance and constant locality. And those are known to exist with independent checks, and that's quite easy to show. Yes, this is an important but non-restrictive caveat for us. So what are the applications of this result? So we've generalized Hastings' result to every classical code with independent checks. And so the first thing to say is just that in future, this can be applied to any quantum locally testable code that needs to be distance balanced. It can now be distance balanced with a good classical LDPC code rather than just a repetition code. But what are applications that we can already foresee based on things that already exist? Well, the most obvious one, but I don't think the most interesting, is to improve the theorem 1.3 of Cross et al. And that was because they, as I say, they distance balance their theorem 1.1, but they do it with a repetition code, and that means that their dimension stays as theta n. So while their physical qubits grow theta nl, their dimension is going to stay as theta n, and the reason for that is the repetition code has dimension 1. Whereas if you use a good classical LDPC code, then your dimension is going to keep scaling as theta nl, so it's going to stay linear. So we get this improvement here, but I think the most interesting application of our result is to this idea of double distance balancing. So double distance balancing, the idea here is if you've got any quantum CSS code, and it could have fairly even distances, it doesn't need to have imbalanced distances. It has, let's say it has fairly even distances, then you can raise one of the distances at the expense of the other one, and then raise that other one at the expense of the first one. So you distance balance one way, and then you distance balance the other way. And so it sort of appears that you're not really doing anything. Why would you do that? But the point is that in taking that product, you are raising the dimension of the code. Because you are doing this with such a good classical LDPC code, you are introducing logical qubits into your code. So the dimension actually rises. This process will also cause the distance to tend towards a square root. If it starts above, below, or at a square root, it will go towards a square root. The locality will be maintained. In some niche cases, the locality might improve, but we would normally just say the locality is maintained. And now we have a lower bound on the soundness under this double distance balancing procedure. Allow me to mention the phrase double distance balancing hasn't been used before to our knowledge, but this is a name that we're going to give it just so we have something to refer to it quickly by. It has been used before, say, for example, here, but we're just going to give it this name for now. So we now have a lower bound on the soundness, and what this means is that any quantum locally testable code, existing or ones in the future, can be turned from what it currently is, which is one quantum locally testable code, into a whole collection. And I like to say that that means that it can be turned from a point in parameter space to a line in parameter space, using this double distance balancing idea, where we distance balance one way and then the other way with a good classical LDPC code. And so the thing that we're going to apply this to show our remaining parameters that we obtain is going to be the hemicubic code mentioned earlier. So these were the parameters here. And then we do 2 distance balancings, one way, one the other way, with a good classical LDPC code of length L. And turning capital N into little n here, we obtain these parameters. This is the general collection that you obtain. So because you're doing distance balancing twice, you incur an L squared increase to the number of physical qubits and an L squared decrease to the soundness. Similarly, the dimension goes up by 2 factors of L. The distance, each distance gets improved by, in absolute terms, by a factor of L on each side. And that then remains the square root of that. And so the square root distance all the way across is just preserved. And then the locality is also preserved, as mentioned. And so we can provide some examples of this collection by setting L to be certain things. So for example, if we set L to be square root of log little n, then you get these parameters. And if you set L to be little n to the alpha, then you get these parameters. This would be like a log length example. This would be like a polynomial length example. And so these are all new parameters for qLTCs. And the last thing to mention is that this gives codes with this condition, soundness times distance over locality greater than a constant. It gives those with a dimension all the way up to, but not including square root, where the previous best was a constant. So in that specific parameter regime, if you want to consider that specific parameter regime, we now get much higher dimension codes. As I say, future quantum locally testable codes can also have their dimensions raised using this idea. So thank you very much for listening. I'm sorry about the problems with the sound. Hopefully we can work those out. But thank you for listening, and I'm happy to take any questions that you have. Leandro, you have your hand raised. I'm afraid I still don't know what's going on with the sound.
Can you hear me?
Adam?
Yes. Hi. Now I can hear you.
Oh, okay, great.
Yeah.
Perhaps the earphones?
Yeah. No, I think it was the headphones.
Okay. Well, thank you for the nice presentation that you gave to us. As Adam said, does anybody have any further questions?
Stunned silence.
Yeah, I think the audience may be very satisfied with your presentation. It was pretty complete. So if we do not have any questions, I'll end it here. I'll stop the recording. And just thank you again for agreeing to come here and talking to us.
Thank you for having me. I appreciate the opportunity.